Okay, so this is the review for the physics test. So it's chapter 5 and chapter 6, and chapter 5 is energy. So we basically said that conservation of energy says that you neither create nor destroy energy, you just change to different kinds of energy. We had, on the left-hand side of the equation, we had the non-conservative work. So non-conservative work, the most prevalent one is friction. And then on the right-hand side, we had that we had the change in kinetic energy. We had the change in gravitational potential energy, and we had the change in spring potential energy. And these two are examples of conservative work. So as you move an object through a gravitational field, you do work. So if you move it away from the point, if you increase the distance between two objects that are being attracted to each other, you increase the potential energy. And if you decrease the distance between the two, then you decrease the potential energy. Now, spring potential energy is also what's associated with conservative work, which are associated with conservative forces. And again, if you compress a spring, then when the spring uncompresses, you have the force in the same direction. And so we just pulled these out because they are something that we see quite often. There are other cases of conservative work, but we haven't really dealt with those. Now, each one of these, what we did was we said the conservative work that we look at, and I guess there's going to be end up being a negative quantity. So the work, the non-conservative work, we'll just say NC, is equal to negative the friction force times the distance through which the friction force acts. So for positive delta x, you're going to get a negative work. So you can see if there's friction, you're going to decrease the kinetic energy, you're going to decrease the gravitational potential energy, you're going to decrease the spring energy. If there is no non-conservative work, meaning there's no friction, then these things add up to 0. Now the friction force is going to be equal to the normal force times the coefficient of friction. And the normal force is equal to the y component of the weight. So if you're on a flat surface, these are the same thing, but if it's on a inclined surface, then you have to take into account the angle. Okay, so the weight is a force times the coefficient of friction times delta x. And W sub y would be equal to the weight times the cosine of the angle that the weight is on, if it's on an inclined plane, times mu, the coefficient of friction, times the distance. This delta x is really, probably should be delta s, so let's go ahead and put that on there. If it's on a flat surface, it's delta x, but if it's on an inclined surface, it's delta s. And finally, the weight is always the mass of the object times acceleration due to gravity. So there's a lot of parts: mass, acceleration due to gravity, angle of the incline, the coefficient of friction, and the distance along here. And what you have to remember is that, if you have an inclined plane like this, that delta s, say, would be this distance along this wedge. And a lot of times you want to relate that to the change in elevation. Say h. Just say, well, it depends whether it's going up or down, so we'll just say it's delta h. And so this is just a triangle. So what you have is that delta h equals delta s times the sine of theta, because this is the opposite side. This is the hypotenuse, so it's going to be the sine. So you end up with the cos. If you deal with these things on an inclined plane, you end up with dealing with the cosine of theta here, and the sine comes in where it relates the change in height to the distance. Okay, so that's the non-conservative work. Then you have the change in kinetic energy, which is 1/2 the mass of the object times the final velocity squared minus the initial velocity squared. Now, we know that when v equals 0, that the kinetic energy equals 0, and the units are going to be, well, energy is Newton meters or joules. So when it's not moving, you have 0 kinetic energy. So if it's initially moving, then and the final velocity is 0, then the final kinetic energy is 0. If it's initially stationary and then then it starts to move, then the initial kinetic energy is 0. So that's why I didn't put a subscript. It all depends upon if it starts from rest or ends at rest. Then you have the change in gravitational potential energy. So that's the mass times the acceleration due to gravity. These are both positive quantities. And then you have h final minus h initial. So if h final is greater than h initial, we have a positive change in kinetic energy. And if h final is less than h initial, then we have the kinetic energy change will be a negative sign. So I'm just putting this in here because, you know, if you do a problem and you want to think, if you're dealing with the science correctly, just think about what's happening. If something's moving up from beginning to end, then you should have the kinetic energy should be positive. And that makes sense because here h final is greater than h initial. You get a positive quantity here. Okay, so that's the energy associated with position. And then finally you have the change in spring potential energy, and that's equal to 1/2 k times x final squared minus x initial squared. Now this x is the spring deflection, and that is units of meters. The units for k is the spring constant, and the spring constant has units of newtons per meter. It says if you compress a spring, what's the resulting force? And that's based on what we call Hooke's law. So force is equal to kx. So if the spring is initially uncompressed, there's initially no force. And then finally the spring is compressed a certain amount, then the force. Now you got to be a little careful about the sign here, but you really don't have to worry about that when it comes to spring potential energy. So you know, remember what we did. You know, the procedure is you write out the full form, okay, and then you get rid of what you can't. So if it says frictionless, that means that the non-conservative work equals 0, so you can get rid of that. If it says a flat surface, so if something's moving on a flat surface, then that means H final equals H initial, or that the change in gravitational potential energy is 0 joules. If it doesn't mention a spring, so no mention of spring, that means that the change in spring potential energy equals 0 joules. And if the initial velocity equals the final velocity, now they don't have to be both 0, they just have to be the same. One special case is when it starts at rest and it ends at rest, and there's 0. So think of bungee cord. So those are the cases where you can get rid of at least one. A lot of times you can get rid of 2 of the terms. So what are some examples? Well, yeah, the bungee. There we would probably say that it's frictionless. So for the bungee cord case, the non-conservative work equals 0 joules, and the change in kinetic energy equals 0 joules. If you block sliding on horizontal surface, or anything sliding on a horizontal surface, so it's sliding. So we couldn't say friction is equal to 0, or if it would just, nothing would happen, just keep going at a constant velocity. So when you've got it sliding and there's friction, then in that case, because there's no mention of spring, the spring potential energy equals 0, and there's no change in gravitational potential energy because it's flat, horizontal. So you get rid of those 2. Then you could look at a block sliding on a frictionless surface running in to a spring. So there you're talking about, here's something sliding along. It's going to be going at constant velocity, and then it hits a spring, and the spring compresses. So under those circumstances, you would have that a couple of things. One is there's no change in gravitational potential energy. Because it says frictionless, there's no non-conservative work. So all you're left with in this case is the change in kinetic energy balances the change in spring potential energy. Also, you may have the case where V final equals 0 meters per second. If it comes to a rest, then you'd use the final velocity 0. If I asked you to say, this is moving at 5 meters per second, how far does the spring compress when the velocity has been reduced to some value? Then in that case you'd have both initial velocity and final velocity, but these things would still be true. If you have something going up incline like this, so it's kind of like the second problem, block sliding. So what you have is you have some movement up here, delta S, and you're going to have, some change in height, H final minus H initial, which is going to be positive in this case. So what you have is this block. It's going to slow down until it stops, or it's going to slow down to some value. Just like here, you can slow down to some value, but not necessarily stop. And there is friction there is a change in gravitational potential energy as this thing moves up, and there is a change in kinetic energy. So, you'd end up with minus mg sine of theta. So that actually it's mg cosine of theta, because that gives you the y component, or the the y component of the force, y being this way upward, so this being x. So this would give you the component of the weight perpendicular to the surface, and then you'd multiply by the coefficient of friction, so that would give you the friction force, and then you'd multiply by delta S. So that would be the non-conservative work. Let's go back, make sure that makes sense here based on what we had here. Negative mg cosine theta mu delta S. Okay, so then you'd have that, and that would be equal to the change in kinetic energy, which would be 1/2 m times v final squared minus v initial squared. So that's the change in kinetic energy. And finally, you'd have the change in gravitational potential energy, which would be mg times h final minus h initial. If it's sliding up, delta S is going to be positive, and this is going to be positive. If it's sliding down, delta S will still be positive, and this would be negative. So you just got to think about what's going on here. So we have this relationship. If it's going up the ramp, then delta S is equal to h final minus h initial divided by the sine of theta. So that comes from this relationship here. So delta H is delta S sine theta, or delta S is H divided by sine theta. If it's going down the ramp, then delta S is going to be H initial minus H final divided by the sine of theta. So, delta S is always greater than 0. And H final minus H initial is, if you're going up the ramp, it's positive. H final minus H initial, you want this to be positive. If it's going down the ramp, we still want this to be positive, so we have to switch the directions. So look at the homework problems, what we did in class. It's going to be one of these kinds of combinations of situations. The only one that I didn't cover, which is if I had a spring here, as this thing, let's say it slid down the ramp and hit a spring, and how far would the spring compress? That would have all four things. It's not that it would be impossible, but I'm not going to give you that one. You could also have, this sliding down if this were sliding down, but without friction. So if the same situation as we just talked about, except that there is no friction, except frictionless. So what happens? Well, let's say I start at rest and I let it slide down. It's just going to accelerate. It's going to speed up, depending upon how far down the ramp we go. But as far as the equation is concerned, the only difference is that the case of frictionless means that this coefficient of friction is 0. So you end up with 0 is equal to 1/2 m v final squared minus v initial squared plus mg times h final minus h initial. So it's just a special case of that. If it were sliding up, you do have to still worry about this relating delta S. Well, no, actually, in this case, you don't have to worry about delta S, because the delta S associated with the friction term. So if there's no friction, you don't have to worry about, you just basically, what do you do here? Oh, well, you don't need delta S, so you just have to figure out what the height difference is. You do have to relate that, so I guess that's still true. So yeah, these are still true. Why do I keep thinking it's not true? Yeah, okay. So I might specify delta S. This block slides down 10 meters. So if I specify delta S, you need to calculate H final at minus H initial and make sure the sign is the correct way. So if it slides down the ramp, and I say slide down the ramp 10 meters, that means 10 meters. Then it's going to be H final is going to be smaller than H initial, so you're going to have a negative sign here. But if it slides up the ramp, then you want this to be positive. So just have to be careful of signs, I guess. Be careful of signs when relating H final minus H initial to a specified distance sliding. You still use these equations here. You still divide by the sine of theta to relate these two things. Okay, so that's it. And then chapter 6, which is we're pretty much limiting ourselves to conservation of a momentum. What that means is we're talking about collisions of some sort, or uncollisions, like a gun and a recoil. So there really are four cases we're talking about. Okay, one is an inelastic collision. So that's where two things run into each other, and the final velocities of the two objects, say object A and object B, are equal to each other. So what comes out of this is you have m sub A times v sub A initial plus m sub B times v sub B initial equals m sub A times v sub A final plus m sub B times v sub B final. So this is assuming we're having two things run into each other. A lot of times VB initial is 0, but not necessarily true. I might just do a different, give this a velocity other than 0. So it's, and you typically are given the initial velocities of the two things and the masses of the two things. You have to calculate the final velocity. So what you can do is substitute V final for each one of these and then figure out what it is. If I asked you to find the change in kinetic energy, which would be, you'd have a decrease in kinetic energy, you'd have 1/2 times the mass of object A times V A final squared minus V A initial squared. So this is the change in kinetic energy of object A. And then you have 1/2 the mass of B times the velocity of B final squared minus velocity of B initial squared. And you can find all this stuff from here. So once you've calculated the final velocity, you can use that in both places here, and then you have your initial velocities. And for these types of collisions, the change in kinetic energy is always a negative quantity. You're always going to lose kinetic energy, and it's going to become heat. Okay, the next one is just an elastic collision, which means that they don't end up with the same final velocity. So V final A does not equal V final B. 99% of the time. I could come up with a case where they might both be 0, but it would be kind of unusual. So it's just to say it's in contrast to the inelastic collision where they are always equal to each other. I'll say V final A does not equal V final B most of the time. And any time that we would consider this. So the conservation of momentum equations don't change at all. The difference, well, it does change because V final, well, these don't change, but there's that additional stipulation that the two velocities, final velocities, are the same, does not apply anymore. So, you know, what you've got to do is you've got to specify one more piece of information because you don't have this extra relationship. So you've got to specify everything except one of the quantities, and so that you know everything except, say, final velocity of A. I'd have to give you the masses and the two initial velocities and one of the other final velocities. Now there is a quantity we didn't discuss in class that sort of tries to quantify how elastic the collision is. And I probably will mention that in class before the test, but I'm not going to put it on the test. And so the change in kinetic energy, if I asked you to find out the change in kinetic energy, which again, unless the collision is perfectly elastic, there is going to be a change in kinetic energy. Most of the time, it's these, because of the elasticity involved, it's going to be a more efficient collision than an inelastic collision. That's kind of the most inefficient way of doing it. But the change in kinetic energy would still be negative here. Then you have the perfectly elastic collision. So this would be ideal springs or maybe a magnetic field. So again, the conservation of momentum equation looks exactly the same. So I'm just going to copy that over. Whoops, I need to do that. So let's just group those together. Copy it. Paste it. Okay, so there it is. Same thing. And then there is the conservation of energy equation, which of course I forgot what it is, so I'm going to look it up in my book. And let me use my new book instead of my old book. Oh, here it is. So it's it's the difference between the velocities. I can't remember whether it's the initial, final. So anyway, we'll look it up here. So, pardon my taking time here. Completely elastic collisions. There we go. So it'll be okay, so here it is. So you can see it's the relative velocity between the two objects finally is equal to negative the relative velocities between the two objects initially. So, as you remember in class, what happens is typically you're given 2 out of the 4 velocities, or I could give you 3 out of the 4 velocities and 1 mass, or it's any combination, so that I end up with 2 unknowns. And now I can't have the 2 masses be the unknowns, because it's really the relative masses that make the difference. But if I could give you 2 velocities and 2 masses, I could give you 3 velocities and 1 mass. I can't give you just 2 masses. So anyway, the idea is you just plug in what you know, and then you have 2 equations and 2 unknowns. You can solve for the, use substitution. So typically use this equation to solve for whatever one of the 2 unknowns. Plug that into here. This will then make this equation 1 unknown. You solve for that, and then you use the value that you calculate here in this equation to calculate the second unknown. So I'm not telling you which ones I'm going to tell you. It could be any of those combinations. So here a lot of times you're given V sub A initial, you're given V sub B initial, you're given the 2 masses, and from that you can calculate V sub A final and V sub B final. But I could also give you V sub A final, and I give you B sub B final and the 2 masses, and then you could calculate V sub A initial and V sub B initial. Or I could give you V sub A initial and V sub B final and the 2 masses. And what I don't know is V sub B initial and V sub A final. But as long as I give you, there's 6 quantities here, the 2 masses, the 4 velocities, as long as I give you 4 out of the 6, then, except giving you all the velocities, but as long as I give you, so I could give you velocity of A initially, the velocity of B initially, the velocity of A final, and the mass of object B, and then you could calculate the velocity of B final and the mass of object A. So and you can see, once I plug the numbers in here, what I know, I'm still going to end up with 2 equations and 2 unknowns. So just be prepared for anything. I may do something, a little bit unusual, but as long as you get 4 out of the 6 known, then you can solve for the other 2. The other thing is you've got to, specify the sign of these. So, if it's left to right, then it should be a positive quantity. If it's right to left, then the velocity should, you were talking about here velocities. So if I said object A is moving from left to right, it should be plus. If the object is moving from right to left, then it's negative. And that should be reflected in these values here. And then when you calculate them, if the answer is positive, then that means the object's moving from left to right. If the answer is negative, then you're moving from right to left. So just think about, make sure you know what you're doing there. Of course, the masses are always positive. So this is just to do with the signs. And this is because we're defining, we're kind of default defining going from left to right as positive. And then the final one are these explosive collisions. And what's an explosion? Well, it could be a spring uncompressing So it's initially compressed and then it uncompresses. It could be, a gun and a projectile. So this is the gun. The gun could plus the person. So typically the person is still holding onto the gun at the end. So initially you start with the gun, a person, and the bullet. And then at the end you have the gun and the person together and the bullet going one way. So the thing about these explosive collisions is that the initial velocities are equal to 0 meters per second. So conservation of momentum just says that there's no initial momentum, so you have m sub a times v sub a final plus m sub b times v sub b final equals 0. And so, the masses are positive, so if one goes one direction, the other goes the other direction. So, the final velocities have to be going opposite directions. So if one's positive, the other one has to be negative, such that the sum of the momentums. And we talked about gases and stuff, but typically in this case we'll have a bullet that's moving at some speed, and we'll have the gun and the person being sent the opposite direction. Or in case of a spring, you'll have two things that are together initially, and then they'll both go either way, like that, depending upon the relative masses of the two. The one that has a smaller mass is going to be moving faster than the one that has the initial mass. The smaller mass, the one that has a smaller mass will be moving faster than the one that has a larger mass. So that, this case, we just know that we're usually solving for these velocities. So if we say one's positive, the other one has to be negative. So those are usually pretty easy. So I think that's pretty much it. It's much more straightforward than chapter 4, because we don't have to worry about vectors. We still have to worry about friction, but we don't have to worry about vectors. Here we do worry about vectors, but we're not dealing with glancing collisions. And we're also not talking about impulse in the test. We're just talking about collisions, inelastic collisions, or perfectly inelastic collisions. That's where these equal each other. Then there's elastic collisions. That's where they don't equal each other, but you have to specify one additional piece of information. Perfectly elastic means that there's no energy lost during the collision or before and after. Now remember, this is the case where you can have a decrease in kinetic energy as you're going through the collision, but that kinetic energy has to be stored either in a magnetic field or in a spring during the collision, and then it's recouped. And once they go apart again, then all that kinetic energy that's stored in the magnetic field or in the spring is then recouped into kinetic energy. And then finally is the explosive collisions. So hopefully that helps you out.